Hello everybody, welcome back to episode 3 of the Math SAT Prep series, where we are going to attempt to go through every math problem from the publicly available paper practice tests on the College Board website. So in episode 3 we're going to start with question 12 from practice exam number 1, and we're going to move all the way through question number 16. So we're starting to build up in complexity here, and just to keep these videos about 15 minutes or less, we're just going to hop right in. So this very first question, we're given a graph of a curve, and it says the graph of y equals f of x is shown, where the function f is defined by f of x equals ax cubed plus bx squared plus cx plus d. So they are giving us a cubic polynomial here. They're telling us that a, b, c, and d are constants. A lot of times I feel like sometimes students get confused with this language, but basically they're just telling us that a, b, c, and d are going to represent some fixed values in this function, and then they ask for how many values of x does f of x equal 0. So remember, when we have the entire function f of x, they're not telling us 0 is the input, they're telling us 0 is the output. Right? So they're asking us for how many inputs is the output to the function 0. So I'm going to zoom in on my graph here, and I'm going to highlight all of the places where I see outputs that are 0. So remember, on the y-axis, that's where we're going to locate all of our outputs. I want to find outputs where y is 0, or places where this function touches the x-axis. Remember, everywhere along the x-axis has a y-coordinate of 0. So I see an output value of 0 here at x is -1. I see an output value of 0 here at x is 4. And I see another output value of 0 here at x equals 7. So for this particular graph, it looks like we are going to be looking at 3 input values, or 3 x's, that have output values of 0. And that one is that simple. So then we move over to number 13. Vivian bought party hats and cupcakes for $71. Each package of party hats cost $3, and each cupcake costs $1. If Vivian bought 10 packages of party hats, how many cupcakes did she buy? So this one, I think on purpose, they kind of write it out to make it look like it's going to set up to be a system of equations question, but actually it's just a simple linear equation that you have to solve, right? So let's just define some variables for ourselves really quick, because they haven't done that for us, right? So we buy party hats and we buy cupcakes. So let's let P equal the number of packages of party hats and let C equal the number of cupcakes that we buy. Cupcakes. I'm writing with my finger here, so excuse my marginally at best handwriting. So to follow through on this equation here, right, they tell us that party hats cost $3. So we know she spent $71 total. The party hats cost $3 and the cupcakes cost $1. So our equation to come up with our total cost should be $1, right, times the number of cupcakes that I bought, plus $3 times the number of party hat packages that she bought, and that should equal $71 total. So just to simplify it real quick, we can have 1C plus 3p equals 71. And then they tell us in the question, we bought 10 packages of party hats, and then we ask how many cupcakes are there. So let's substitute in 10. We know that the number of party hat packages is 10. So I can have a new equation now that just says $1 times every cupcake plus $3 times our 10 packages of party hats should equal the $71 that we spent total. So we end up with the number of cupcakes plus 3 times 10, which is 30, is going to equal the $71 we spent total. And if I subtract away 30 from each side, I'm going to get that each of my cupcakes, which each costs $1, right? There should be 41 cupcakes. If I spent $41 on cupcakes plus the $30 I spent on party hats, that will give me my $71 total. And that's it for number 13. Now, number 14, another heart of algebra question here. What is one of the solutions to the given equation? So they give us a quadratic trinomial, z squared plus 10z minus 24 equals 0. It's already set equal to 0 for us, which is nice. And they're going to ask us to go ahead and solve. All right, and if you're familiar with these, you know that in order to knock these out, you have to factor and then solve. Alright, so there's our equation. We're going to factor this one using the product sum method. If you're not familiar or up to date on your factoring, we know that we can use product sum method here because I have a quadratic trinomial with a leading coefficient of 1. Notice there's nothing written in front of the z squared. And so what I am going to look for is I'm going to try and think, well, what two numbers could multiply to negative 24 and add to 10? I also know that for quadratic trinomials, they're going to factor into the product of two binomials. And if my first term on this quadratic is z squared, then the first term in each of my binomials should be z. And now in these blank spaces here, I'm just going to fill in what two numbers can I think of that are going to multiply to negative 24 but add to positive 10. So I'm thinking positive 12 and negative 2. Those will multiply together to give me negative 24, and they will add together to give me positive 10. And then I'm going to apply my zero product property here, right? I can set each one of these individual factors or these individual binomials equal to 0 because 0 times anything is always 0. So if I can find a value of z that makes one of these binomials equal to 0, then the whole equation is going to go equal to 0. And so if I have z plus 12 equals 0, then one of my solutions is going to be z equals negative 12. And the other solution is going to be z equals positive 2 by adding 2 to both sides. You only needed to give 1. And if you got this question in the calculator section, you also could have just graphed this. You could just plug in x squared plus 10x minus 24 into your graphing calculator, hit graph, and then look at the table and find one of the x values that is associated with a y value of 0. So that's number 14. Number 15, they're going to give us an exponential functions question. So it says bacteria are growing in a liquid growth medium. There were 300,000 cells per millimeter during an initial observation. The number of cells per millimeter doubles every 3 hours. How many cells per milliliter will there be 15 hours after the initial observation? So what I need to think here first before I do anything else is I need to figure out, well, how many times are my initial 300,000 cells going to change or grow according to whatever growth factor they've given me. Now the growth factor they've given me is doubles. So when I think of doubles, I think times 2. So I'm going to take my initial 300,000 cells and I am going to double it. But how many times am I going to double it? Well, they tell me that 15 hours are going to go by and I am going to double once every 3 hours. So how many times am I going to double total? Well, if I double every 3 hours for 15 hours, I should double 5 times. So you don't actually really need to know much about exponential equations to get this one right. You could just think I need to take my 300,000 and multiply it by 2 times 2 times 2 times 2 times 2. There are my 5 doubles. 1, 2, 3, 4, 5. Now the reason this one can be called an exponential equation, well, actually we'll get to that in a second. We're going to take our 300,000 and that is going to double 5 times. Raise that to the 5th power. We're going to multiply by 2 5 times. So that's what an exponent of 5 represents, the number of times we're going to end up multiplying by 2. The reason this would be considered an exponential equation is because if I didn't know how much time had gone by total, I could rewrite this as 300,000 and we are going to double. How many times are we going to double? Well, over the course of t hours, we're going to double every 3 hours. So if I plug in 15 hours for t, then my exponent will be a 5. 15 divided by 3 is 5. If I plug in an 18 for t, then my exponent will be a 6. That means I've doubled 6 times. And whenever the variable is in the exponent's position, you have an exponential function. Now, we didn't need to go that detailed here. We just needed to figure out what is 300,000 times 2, 5 times. So you could write this out on your paper, or you could just do it in your calculator. So we're going to take 300,000 and we're going to multiply it by 2 once, twice, 3 times, 4 times, 5 times, and if you do it in your calculator, you are going to come out with 9.6 million, or 9,600,000 cells, which is answer choice D. Last one here. Make our space. Alright, last question here. They're asking us which expression is equivalent to 6x to the 8th plus y squared plus 12x squared y squared. So basically, all they're asking us to do is just kind of play with this expression up here that they've given us and see if we can come up with one of these expressions that matches. Now, when I look at this, I might be thinking to myself, okay, well, how can I manipulate this expression up here? Can I combine like terms? Can I add these two terms together? And the answer to that question is no, right? In order to add like terms, the terms themselves, right, if I wanted to add this 6 and this 12 together, I need to be attached to an expression that has like bases and like exponents. And we don't have that here, right? I actually do have like bases. They each have an xy, but the exponents are different, right? This first term has an x to the 8th y squared, and this second term has an x squared y squared, which means these are not like terms and they can't be added together. So instead of trying to combine these two pieces together, let's see if I can actually factor. So I think actually these two terms do have some pieces that are in common. I think I could factor out a 6, right? Because 6 goes into both 6 and 12. And now I'm looking at my bases and my exponents and I'm trying to figure out, well, how many x's and how many y's does each side have in common? And it looks like if this one has x to the 8th and this one has x squared, I can probably factor an x squared out of each term. And then they both have y squared, so I should be able to factor y squared out of each term. So we said I can factor out a 6, I can factor out an x squared, and I can factor out a y squared. And if you're not following how I know that, let's just try and break these two terms down, okay? So I'm going to try and break these down into the smallest pieces possible, and then I'm going to pull out all of the pieces that are in common. So when I think about 6, I think I can break 6 down into 2 times 3. And x to the 8th, an exponent of 8 means I'm going to multiply x by itself 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Whoops. There's my 8th x, and then I also am going to have y squared. So y, let's move over a little bit, and y. Okay, so here's my, if I were to multiply all these pieces together, I would have 6x to the 8th y squared. Now maybe in a different color, I'll break down 12x squared y squared, right? So how do I break down 12? Well, I can break down 12 into 6 and 2, 6 times 2, but then I can break 6 down again into 2 times 3. Let's make a better 3. That didn't work. So if I want to break down 12 into the smallest units possible in terms of multiplication, I can break 12 down into 2 times 2 times 3, and x squared I could break down into x times x, and y squared I could break down into y times y. And then what I'm going to do here is I'm going to find all of the common factors, right? I'm going to find all the pieces that are in common. So maybe I'll highlight them now in yellow. So I see my first term that I broke down in red has a 2, and my second term that I broke down in purple has a 2. My first term that I broke down in red has a 3, and my second term that I broke down in purple, has a 3. They each have 2 x's being multiplied together at the very least, and they each have 2 y's being multiplied together at the very least. So this tells me that I can factor out a factor of 2, a factor of 3, a factor of x, a factor of x, a factor of y, and a factor of y. So if I multiplied that together, 2 times 3 times x times x times y, I would get 6. Oops. Go back to using my finger. I would get 6x squared y squared. I'm going to try and get better styluses so that I can write better. I've bought several different types of styluses, and each of them has their own problems. So we're just going to stick with the finger for now. But now what I have to do in parentheses is I have to remember all the pieces that got left behind, right? So these I factored out. So what's left over? Well, from my first term, I have 1, 2, 3, 4, 5, 6 x's. So if I were to multiply those all together, I would have x to the 6th power. We're going to remember that we were adding these two terms together, so we'll bring down our plus sign. And what is going to be left out of our second term? Well, it looks like we factored out the 2, the 3, the x, the y. There's just one lonely 2 left over. So when factored completely, this thing looks like it factors down to 6x squared y squared times x to the 6th plus 2. That looks like it would be answer choice C. And that's about enough for today. If you want to do a private SAT prep session, or if you're struggling in any of your other math classes, you could always book a session by visiting my website, physmatics.com. You can find the link in the bio for my YouTube channel. Thanks for listening. Bye.